Part 3. Question 7. Part A. The force that keeps an object moving in a circular path is known as the, well, it's centripetal force. So I guess you either know it or you don't. Part B. Figure 7. Part B. Figure 11 shows an object moving in a circular path. Part 1. Draw an arrow on figure 11 to show the direction of the force, so that's the centripetal force, that keeps the object moving in a circular path. So the object will go flying outwards like this, except there's a force pulling inwards towards the centre. So that's the centripetal force. And this force always acts in towards the centre. So if this ball, if the planet was over here, then the force would be acting in this way. If it was here, it would be acting in this way. Sorry for that being a bit wobbly. Part 2. The object in figure 11 is moving at constant speed. Explain why it is not moving with constant velocity. So you've got to know the difference between speed and velocity. So speed is a scalar and velocity is a vector. A scalar has only size. A vector depends on size and direction. So, since the direction is constantly changing because it's going around in a circle, its direction's constantly being nudged back in towards the centre. That's why the velocity is constantly changing, because the direction's constantly changing. Question C. Figure 12 shows a skier on a slope. The skier travels down the slope with a constant acceleration. The speed of the skier is measured at points P and Q. The table in figure 13 gives some data about the skier making one downhill run. So we know the acceleration, we know the speed at P, and we know the speed at Q. Calculate the distance from P to Q. So calculate the distance. Use an equation selected from the list of equations at the end of this paper. Oh, well, it's that one. We know the final velocity. So that's at the bottom of the hill. We know the initial velocity at the top of the hill. It gives us the acceleration and we need to work out the distance. So, and it's a velocity squared, by the way, and in both cases. So the final velocity squared, v squared minus u squared equals 2ax. X is the symbol for distance. So what I'll do, I'll write in, that's A for acceleration. Speed at P, that's at the top. So that's the initial speed, U, initial velocity, sorry. And Q is the speed or velocity at the end. So that's V. And it's V squared minus U squared equals 2 times by the acceleration times by the distance x. So I've got to rearrange that in order to find x. Well, an easy way of doing it, if you do a line on both sides, whenever you've got to move something from one side to the other side, it's got to cross over the line as well. I'll show you what I mean. Right, we want to get x by itself. It's already on the top, so that's great. So A, when it comes over to the other side, it's got to come down the bottom here. And when the 2 comes across to the other side, it's also got to cross the line, so it's also got to go down the bottom. Okay, so we end up with x equals v squared minus u squared over 2a. Pop the numbers in. And that equals 86.37. Part 2. Calculate the time taken for the skate to travel from P to Q. So what do we already know? Well, we've got the acceleration, we've got the speed at the start, and we've got the speed at the end. Acceleration, speed at the start, u, speed at the end, v. So we can just use this equation. Acceleration equals v minus u all divided by t. Now we need to rearrange that equation. So we'll do it the way we have been doing it, which is to put a line here. And remember, if something moves across to the other side, then it needs to also cross the line. So the first thing is we need to get t by itself, but we also need to make sure we've got it on the top. So the easiest way of doing that is to take t across to the other side, because then what we'll have to do is we'll have to put it up to the top. It's got to cross the line, remember, when it moves across the bridge. So that'll end up there. Cancel that. And then we need to move a across to this side. And remember, because it's crossed the bridge, it needs to cross the line as well. So that'll come down to the bottom. If I rearrange that, or if I just write that out again so it's nice and neat, and then put the numbers in, and that comes out as 5.46 recurrent, and we'll just round that up to 5.5. Question number 8, part A. Energy from the nuclei of atoms can be used in medical diagnosis and treatment. Fluorine-18 is a radioactive isotope used in PET scanners for medical diagnosis. Explain why fluorine-18 must be produced close to the hospital where it is used. Well, whenever you're using radioactive isotopes on patients, they need to make sure that they've got a short half-life. And if they've got a short half-life, wherever they're being made, they need to be able to get it to the hospital quickly so that it's still got enough radiation and it'll be effective for the treatment. Part 2. Some tumours inside the body can be treated by using either alpha radiation or gamma radiation. Explain why the source of alpha radiation is used inside the body, but the source of gamma radiation can be outside the body. Now that's to do with the penetration powers. Alpha is not very penetrating, and it can't penetrate inside skin, so it needs to be placed inside the body next to the tumour in order to treat it. Gamma, however, is very penetrating, so it can be placed outside the body because it can easily penetrate inside the body and get to the tumour. Part B. 1. In a controlled chain reaction of uranium-235, which of these could cause a uranium-235 nucleus to undergo fission? Well, I guess it's either you know it or you don't know it. It's a neutron. A neutron is what we use to start fission. This is the image you need inside your mind. You've got the neutron here. Helps if I spell it right. And it hits a uranium atom, which then splits up into two smaller daughter atoms, plus extra neutrons are emitted. Now those neutrons are each available to initiate further fission reactions on more uraniums. Now at this part, energy is also emitted, and that's the energy that we use in order to turn water into steam. Steam turns a turbine, turbine turns a generator, or rather the energy is used to heat a moderator, which is a liquid. The kinetic energy of one of the particles released in a fission reaction, so I guess that's these little neutrons, is 1.2 times 10 to the minus 11 joules. The mass of the particle is that. Calculate the velocity. So you're looking for the equation for kinetic energy. We've got the mass, we need the velocity. So the equation for kinetic energy is a half mv squared. Now, if I know that I'm rearranging the equation, what I'll actually do is I'll write it as kinetic energy equals mv squared divided by 2, because that's the same as multiplying something by a half. Now let's rearrange it in the same way that we've been using in the past. So if I draw a line here, I need to get v by itself. So I'll take the 2 over to the other side, but remember when it goes to the other side it also needs to cross the line. So the 2 comes on the top, cancel that out, and we need to get the m across to the other side, and remember it needs to cross the line. So there we go, and I'll just rewrite that so it's neat. Now if I pop the numbers in, and that equals 1.714 times 10 to the 14. Now remember, that is not v, that is v squared. So we need to square root it. And that equals 13.09 times 10 to the 6. Now if we give them the number in the way that they've give it to us, where it's just to one decimal place, that would be 1.3. And that would be times 10 to the 7. Question number 9. Some sunglasses have photochromic lenses. Photochromic lenses are clear when the lenses are indoors, but they darken in bright light to reduce the effects of the sunlight. Photochromic lenses react to ultraviolet light. Suggest the benefit of making the lenses go dark with ultraviolet light. Well, it protects the eyes from the UV light. Part B. Radio waves from Jupiter take 40 minutes to reach the Earth. Light waves from the Sun takes 8 minutes to reach the Earth. Calculate how many times further it is from Earth to Jupiter than from Earth to the Sun. State the property of electromagnetic radiation that is used in your answer. So we know that radio waves is an electromagnetic wave, and we know that light waves are electromagnetic waves, and we know that all electromagnetic waves travel at the same speed, the speed of light, in a vacuum, which is what space is. So if we use that, then basically the ratio of the distances and times should be the same. If we know that the speed equals distance over time, and we know that the speed needs to be the same each time, what that means is if the time gets bigger, then the distance must also get bigger by the same amount. So we know that this time here is bigger than this time here. If we do 40 over 8, that comes out as 5. So basically, this is 5 times more time. So that must mean that Jupiter is 5 times more distance away. Question C. Ultraviolet waves cover a range of frequencies. Scientists divide this range into 3 types, UVA, UVB and UVC. The table in figure 14 shows the frequency range for each type. So the frequency range, UVA 7.5 to 9.4, UVB 9.4 to 10, UVC 10 to 30. So the frequencies, what we've got is this is a low frequency and this one is high frequency, and the one in the middle is medium frequency. Figure 15 is a diagram about the effects that the Earth's atmosphere has on 3 types of ultraviolet radiation. So there's the Earth's atmosphere and UVA. You can see how much of each one is getting through. Describe how the effects change with wavelength. Cheeky. So it's giving you information up here to do with frequency, but down here it's asking you to talk about wavelength. Describe how the effects change with wavelength using information from figure 14 and 15. The width of the arrows drawn indicates the amount of radiation that is involved. Calculations are not required. Right, well, looking at the picture, lots of UVA can get through, and that must be, let's talk about wavelengths. So we know that the speed of light, any electromagnetic wave, so ultraviolet is an electromagnetic wave, so we know that the speed is going to be the same, and the wave equation is that speed is frequency times by wavelength. So if C has to remain constant, then if the frequency gets smaller, then the wavelength must be bigger. So this is a small frequency, so that must mean that it's a long wavelength. And if this frequency was to get bigger, then the wavelength must get shorter in order, once again, to keep this value the same. So UVA, it's got a long wavelength, and we know that lots of UVA is transmitted. If we look at UVB, it's got like a medium wavelength and not much is transmitted. And finally, UVC, none is transmitted. And we've actually got a little bit getting reflected. And that's the short wavelength. So lots are getting absorbed of the UVC and some is actually being reflected. Now it's worth 4 marks. If I didn't get 4 marks for that, I could also write in the shorter the wavelength, the less is transmitted. Question D. Radio waves and gamma radiation are at opposite ends of the electromagnetic spectrum. Compare how these two electromagnetic radiations are produced. And it's a 6 marker. Okay, let's talk about radio first. So they are produced using alternating current. And it's the free electrons that are moving backwards and forwards. And they're basically produced by humans. And we can produce them in aerials and electric circuits. Gamma, well, they are produced by radioactive decay. I've got a nice video if you want to click the link above, all to do with radioactive decay. It's produced in the nucleus of atoms when they are attempting to become more stable. Gamma is often released at that point. Question number 10, part A. Stars may originate as a nebula. Describe the process that then occurs to produce the conditions necessary for nuclear fusion in a new star. So, nuclear fusion in a new star. I've got a nice video that covers the birth, the life and the death of stars. Click the link above. All stars start off as a nebula, which is basically a giant cloud of dust and gas. Now gravity starts to make it collapse in on itself, and it brings all the dust and gas together. As they do so, the particles are obviously gaining kinetic energy because they start to move fast, and they start to rub against each other, and the friction of these particles colliding, well, you know what friction does. It makes things get very hot. And also, because the dust and gas is all collecting into one place, it causes the pressure to increase as well. So it gets very hot and the pressure gets very big. Part 2. The energy E released in nuclear fusion is equivalent to loss of mass m according to the equation E equals mc squared. This is just one of those questions where they give you an equation and you've got to rearrange it. C is the velocity of light, that's the value of it. In 1 second, the energy radiated by the sun is that many joules. Calculate the loss in mass of the sun in 1 second. So we just need to rearrange it to find m. So if I just write the equation down here, E equals mc squared. This is Einstein's most famous equation. And I just pop a line under each side as we've been doing whenever we've been rearranging. Now we need to get m by itself and on the top. Well, it's already on the top, so we just need to get it by itself. So if I take this c squared over to the other side, now remember, if it crosses onto the other side, it needs to cross the line as well. So it comes down to the bottom here. And that's all we need to do. So I'll just write it out again so it's neat for the examiner, and I'll pop the numbers in. I'll put that in brackets because I'm squaring it. And that comes out as 4.28 recurring times 10 to the 9. Now they've gave me the numbers with 2 decimal places, so I'll give it back to them with 2 decimal places, and I'll just round up the 8 to the 9. I'm not really happy with that, so I'll just try to write the decimal in again there. I'm just going to write it here because I'm not happy with how clear that was. Part B. Oof, another 6 marker. So we're just coming up to the end of the paper and we think we've got away with it. And then we've got another 6 marker. The Big Bang Theory gives an explanation for the origin of the universe. Explain how evidence supports the ideas that the universe is expanding and the universe began at a single point. So let's consider the evidence for the universe expanding. It's always the same evidence. So we're talking about the redshift, and that is where light from distant galaxies gets shifted towards the red end of the spectrum, making the wavelength get longer. And the universe began at a single point. So if everything's expanding outwards as we go forward in time, if we were to go backwards in time, then the universe would shrink and everything would start from a single point. Now, the Big Bang Theory says that there was a Big Bang, and it was at that point that there was an expansion afterwards. Now, the evidence we've got of the Big Bang is called cosmic microwave background radiation. Now, it started as gamma radiation nearly 14 billion years ago, but as the universe has expanded, the wavelength of the gamma radiation has also expanded, and it's now in the microwave region. And finally, last question, question C. The star has evolved to become a neutron star. The mass m of the neutron star of radius r is given by, and then it's just one of these questions where you're going to have to rearrange the equation by the looks of it. D is a constant, gives you the size of m, gives you the size of d. Use the equation to calculate the value for r. Okay, so we're going to have to rearrange it. So if I just write the equation out again. Now we'll rearrange it how we've been rearranging things. We'll just pop a little line here, because there's already a line on that side. And we need to get r on the top, which it already is. And now we need to get it by itself. So we need to move all of these things onto this side. So if I start with the 3. Moving the 3 across to the side would put it there, but as it comes across to the other side, it also has to cross the line, so it ends up on the top. The 4 crosses across and then moves over the line, so it ends up on the bottom. And the pi comes across and then moves down. And the d also moves across and then needs to move down. So I rewrite that so it's neat. And then we'll pop the numbers in. And that equals 1.59 times 10 to the 12 But remember, that is not r, that is r cubed. So I hope you know how to use your calculator properly, because we need to cube root this number. And that's the advantage of making sure that you take your own calculator into the exam, so you know how to work it properly. You don't want to drop some marks just because you're using a calculator that you've never used before. And that answer comes out as 11.675 times 10 to the 3. Now they've gave us with the numbers just in a very basic form. So if we were to manipulate that, let's turn 7, use this 7 to turn the 6 into a 7. 1.17 times 10 to the 4. And that's it. We are finished the paper. I hope it's been useful for you. Make sure that you like the video, and there'll be some more papers to follow. So work hard, be nice, take care of yourself. Bye for now. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained. Thanks very much, and bye for now.